In this lesson, we're going to talk about patterns and inductive reasoning. Our objective is to use inductive reasoning to make conjectures, and we'll talk about what conjectures are in just a little bit. Inductive reasoning is reasoning that's based on observing patterns. For example, here is a problem where we have some numbers that actually form a pattern. If you look at the numbers 3, 9, 27, and 81, the relationship between those numbers is each consecutive number is multiplied by 3. So we can find any number in that pattern just by continuing to multiply by 3. In this example B, we have a circle that circumscribes a triangle, and then we have a square, and then we have a 5-sided figure, or a pentagon. So the next two things in the pattern would be a 6-sided figure and a 7-sided figure, a hexagon and a heptagon inside the circle. Here's one for you to try. Go ahead and pause the video and see if you can come up with the patterns on this one. All right, in example A, you can see that each of these consecutive numbers are decreasing by 5. So the pattern in that one would be, and I'll go ahead and write this down for you as well, the pattern in this one would be minus 5 each time. To get from one number to the next, you are subtracting 5. And example B, that one, what's happening there is you're taking the midpoint of each side to form the figure that goes on the inside. And this one's kind of small to draw, so you would go ahead and make your midpoint at each one of these sides and draw another figure inside. And that one's going to be difficult. You can go ahead and make that a little bit bigger, because that's going to be difficult for me to draw in the video here. So go ahead and make your figure a little bit bigger, but you can see that it's going to be the midpoint each time. If we had a problem where it said we want to find like the 100th term or the 1000th term, we're certainly not going to want to multiply or add or subtract or do something like that every time to get to the answer. So that's where it's going to be helpful to find a pattern. And when we find those patterns, we can make a conjecture to get the conclusion for each of those problems. So here's an example using inductive reasoning. It says, look at the circles. What conjecture can you make about the number of regions that 20 diameters form? So here we have 3 circles. The first one has 1 diameter, then 2 diameters, then 3 diameters. So we want to take a look at what's the relationship between the number of regions that are formed as we add diameters. With 1 diameter, we have 2 regions. With 2 diameters, we have 4 regions. And with 3 diameters, we have 6 regions. So we can kind of see a pattern going on here. Every time we add a diameter, we get double the number of regions. So if we had 20 diameters and we doubled that, we should get 40 regions. What conjecture can you make about the 21st term in this pattern? RWB, RWB, and it just continues to repeat like that. Well, the 21st term, if we look at that, every third term is a B. And since 21 is divisible by 3, we could conclude that the 21st term should be the letter B. Another thing that's important to make sure of is that we have enough data to make a conjecture. If you looked at the sequence 1, 3, and that's all you had, that's not enough information to go ahead and make a conjecture. So you need to make sure that you have enough information to actually make the conjecture. So here's an example of collecting information to make a conjecture. It says, what conjecture can you make about the sum of the first 30 even numbers? So what you want to do is just write your number of terms. If you start with probably 4 terms is a good number to have. And go ahead and write what the sum of the first 4 even numbers is. So 2 is our first even number. That gives us a sum of 2. 2 and 4 gives us a sum of 6. 2, 4, and 6 is 12. 2, 4, 6, and 8 is 20. Sometimes it's going to be difficult to notice that pattern, but do the best you can. This one we have the answer given to us. It's 1 times 2, 2 times 3, 3 times 4, 4 times 5. So if you look at this pattern, the number of terms we have, we're just taking the term number and increasing by 1 and multiplying by that. So if we want the first 30 even numbers, we don't want to continue this pattern. That would be very labor intensive. So we're going to take 30 times the next highest number would be 31. So that would give us 930 when we multiply that. Here's an example of making a prediction. It says the sales of backpacks at a nationwide company decreased over a period of 6 consecutive months. What conjecture can you make about the number of backpacks that the company is going to sell in May? And we have this all the way through April, and it looks like they are decreasing. And if you look at the graph here, it looks like they're decreasing by about 500 backpacks a month. So it'd be reasonable to say that in May, maybe we're going to have 8,000 backpacks because we have just under 8,500, so maybe 7,900 would be also a reasonable number. Question 4a, what conjecture could we make about the sales in June? Well, we could do the same thing. We could subtract another 500 from that and say maybe 7,500 would be a reasonable estimate of how many backpacks they would sell. For part B, they ask us, is it reasonable to use graphs to make a conjecture about sales in August? Now, the thing you got to think about there is that's back to school time, and so that's usually when the amount of backpacks are going to go up. So probably not. It would not be reasonable to make that kind of a conjecture because that's when they're going to hit their peak sales are probably in August. Something you need to be aware of is that not all conjectures are true. Most of the ones we've looked at were true, but we also have to test those conjectures to see if we can come up with what's called a counterexample. If you can come up with just a single counterexample, then the conjecture is false. You only need to find one. So here's an example. What's a counterexample for each conjecture? If the name of a month starts with the letter J, then it's a summer month. We'll list all the months that start with J. We have January, June, and July, and January is definitely a counterexample that's not in the summer. So January would be our counterexample of a month that is not in the summer. How about letter B? You can connect any 3 points to form a triangle. Well, there's one counterexample. If they're in a straight line, that doesn't make a triangle. So that's all we need to prove that the conjecture is false. Here's 3 examples. See if you can pause the video and come up with an example for each one of these. And then I'll give you the answers when you come back. All right, so if you look at, excuse me, letter A, if a flower is red, it's a rose. Well, what's a flower that's red that's not a rose? You could have a geranium, a carnation. There's lots of different ones that you could put in there to prove that that's false. So I'll just put in a carnation. Should have done it in red. That would have been better. And then how about letter B? One and only one plane exists through any 3 points. Well, although it takes 3 points to determine a plane, if we have 2 planes that intersect in a line, then you could put 3 points that are on that line and they would exist in both planes. So that would be an example. I'm not going to write that one down, but hopefully you're listening. How about letter C? When you multiply a number by 3, then the product is divisible by 6. Well, what if we took 3 times 5? That gives us 15. Is 15 divisible by 6? No, it is not, so that's a counterexample. That one proves that it is false. That is not a true conjecture. And here's your lesson check. Find the next 2 terms in each sequence and bring those answers to class. See you then.